All right, we're going to talk about nuclear chemistry, and at this level of chemistry we talk very briefly about it. We don't go very in depth. So nuclear chemistry, the nucleus of the atom, so we're talking about the protons and the neutrons, decays. So it falls apart or it can fuse with other nuclei. And it does this when there's not a balance between the number of protons and neutrons. So when the neutrons outnumber the protons, it will undergo some type of decay. Now that could be the nucleus spitting out other particles, or it could be giving out radiation, or it could be both things are being released. It all depends on what that ratio is and how big the nucleus is. So decay is a random event. If a nucleus is not stable, then it's going to undergo decay and you can't stop it from happening. So if we had nuclear or radioactive isotopes, we can't put them in a deep freezer to prevent it from undergoing decay. It's going to happen no matter what. So this graph is just showing you the zone of stability, which is this green area. The blue dots would represent stable isotopes, so things that don't undergo radioactive decay. And then you can see some of it's beta, some of it's gamma. This is a little bit more than we actually need to know at this level. When we do talk about decay, though, we are focused on three different types. And so our three different types are alpha, beta, or gamma. So you should pause the lesson right now and copy down this chart, and then we will fill this chart out together. All right, so alpha, when we say the symbol for alpha, we're talking about the Greek letter. So alpha kind of looks like the fish. When we talk about alpha decay in a reaction, it's denoted by the helium-4 isotope. So remember, the number in the upper left-hand corner is the mass, and the number in the bottom left is showing you how many protons there are. So when we say charge, because nuclear chemistry is all about the nucleus, the charge is referring to those protons, so we would say +2. Alpha is very weak. In fact, you're bombarded with alpha particles all the time from the sun, and it doesn't do you any harm. So to block alpha particles, all you really need is something as thick as a piece of paper. So you could block alpha just by anything that's the thickness of a piece of paper. So your skin can block alpha particles. Beta particles, the symbol is B with a tail. That's the Greek letter beta. In a reaction, it's symbolized by 0, -1, E. Notice this E is lowercase, so this is not an element. The mass is still in the upper left, so it's 0, and the charge is -1. All right, so what has 0 mass and a negative charge? An electron. So this is where it gets kind of odd to think about. You have your nucleus, and it emits an electron. And how it does that is the neutron, which is neutral, breaks into a positive and a negative, and that negative can't stay in the nucleus, so it gets spit out. So that's kind of where the beta particles are coming from. Beta just means an electron. Now, it's still considered weak, but you do need something a little thicker than a piece of paper. So you could use a piece of wood or a piece of metal to block it. Kind of like those lead vests that they put on at the dentist office when they do the x-rays for the teeth, or if you were to break a bone and go into the hospital, they put the lead on you to protect your organs when they take an x-ray. All right, gamma is our third one, and the Greek symbol for gamma kind of looks like a scripty Y or an upside down alpha if you want. It's a form of energy. So gamma is simply energy, where alpha and beta are actual particles. So we don't denote them in a reaction at all because it's energy and our reactions just show particles. It doesn't have a mass. It doesn't have a charge because, again, it is just energy. Now, it is very strong. It is the strongest type of energy that we have. So when you think about the nuclear bombs, being dropped in Japan, the gamma energy is what did the most amount of damage. So in order to protect yourself from gamma rays, you would need 18-inch thick lead. So you would have to build yourself 18-inch thick walls, ceilings, floor to protect yourself from gamma radiation. And so that's not something that's actually feasible, which is why we don't want to use nuclear arms when we go to war, or anytime really. All right, so let's look at some of these reactions. You should be able to balance these reactions. So you'll be given some pieces of the reaction and there'll be a piece missing, and then you just have to fill in the blank. Now remember, the top number equals the mass and the bottom number equals the atomic number. So the bottom number is missing here, but we know the element is U, so we can look at the periodic table. Uranium is all the way down here. It's number 92. So we can go back to our problem and we can fill in 92. Helium, we have the mass number, but we're missing that atomic number. So we go back to the periodic table. Helium is right here. It's number 2. So we're going to go take our atomic number and put it down on the bottom. And then it just becomes an algebra problem. Treat the arrow as an equal sign. So you would have 238 equals 4 plus, and then you're looking for this missing piece. So you would do 238 minus 4 gives you 234 as that missing piece. We're going to do the same thing for the atomic numbers. 92 equals 2 plus what? And you would subtract both sides and we would get 90 for X. Now remember, it's the atomic number that is on the periodic table. So we go back to the periodic table and we look for number 90, and they do go in order. So number 90 is down here. TH, so it's thorium. And so we write capital T, lowercase h. All right, for the second problem, again, you're using that mass number on the top, atomic number on the bottom. So we first need to find out what the atomic number of lead is. So we go to the periodic table and we search for lead. It's right here. It's number 82. So we can go back and fill in 82. Now it just becomes the math again. 208 equals X plus 0. So X, the mass number for the missing piece, is going to have to be 208. Subtract 0 from both sides. Now this bottom one is where it gets a little tricky because you got to watch out for that negative. So we have 82 equals X plus a negative 1. Now remember, you can rewrite that to be 82 equals X minus 1. So you end up adding 1 to both sides. And so you have X is equal to 83. And so we go to our periodic table and we search for number 83, and they go in order by atomic number. So 83 is right here next to our lead, which was 82. So we must have formed bismuth, or Bi. So we're going to write capital B, lowercase I. All right, pause and try the other two on your own. Okay, so for number 3, we would need the atomic number of helium again is 2. We take Pa, we go to the periodic table, and we search for Pa. It's down here with thorium, so it's number 91. So this is 91, and then you solve the top and the bottom. Here we have X equals 4 plus 230, so we get 234. And then for the bottom, we have X equals 2 plus 91. So X is 93. And then we can go back to the periodic table, find number 93. It's neptunium. So we're going to write a capital N and a lowercase p. And we have this last one. Again, need to fill in the atomic numbers. 1, 2, and carbon is number 6. Then we can solve the top. So we have 1 plus 4 plus x equals 12. So 1 plus 4 is 5. So 5 plus x equals 12. So if we subtract 5 from both sides, we have 7. And then on the bottom, we have 1 plus 2 plus x equals 6. So 3 plus x equals 6 means x has to be 3. Then we can look on the periodic table, find element number 3, which is lithium, and we get Li. Now, not only should you be able to fill in the blank, but you should also be able to state whether it's alpha, beta, or gamma. So if we go back to the chart we just formed, we are looking for these things in the reaction. Gamma won't ever be the answer because remember, gamma is just energy, so it's not shown in the reactions. So if we see 4,2He, it's an alpha decay. If we see an electron, that makes it beta decay. So in number 1, we have 4,2He right there. So this is alpha decay, and it's always decay. In number 2, we have the electron, so that's beta decay. And then in number 3, again, we have 4,2He, so that's alpha decay. Now remember, we're just skimming the surface of nuclear chemistry. So number 4 is not alpha or beta decay. It's actually a different type of process happening. So if we skip over the periodic table, the last slide for this lesson, fission versus fusion. So fission, division, you're taking that atom, the nucleus, and you're splitting it into 2 lighter nuclei. So fission, division, fusion, combine. So fusion, you're taking 2 light nuclei and putting them together to form a stable, heavy nucleus. Fission, division, fusion, combined. So if we were to go back and look at that last process, that last reaction we had, this would, number 4, we are taking 1, 2, 3 nuclei and combining it into 1. So we're fusing those 3 together. So this is an example of fusion. Now if we were to look at number 3, we started with 1 nucleus and we ended with 2 nucleus, or 2 nuclei. So that would be an example of fission. Number 2 again is not fission or fusion, that's something else. Number 1, we started with 1 nuclei and we ended with 2 nuclei. Sorry, 1 nucleus and ended with 2 nuclei. So that again is fission. Fission, division, fusion, combine. Make sure you try the questions on the Google form and leave me any comments that you have about this lesson.